Lesson 9.2 really introduces us to the next phase in Unit 9. We spent a lot of time on 9.1. It was almost its own little mini unit. And on 9.2 is where we really kick off solving quadratics. Now, we use quadratics in Unit 8 mainly to really understand how the graphs behaved and the different forms of the quadratic equation, like vertex form, intercept form, and standard form. But really, it's not until this 9.2 that we sort of formally talk about all the different ways that you can solve them. So our first lesson of many different options is going to be how to solve by graphing. And this is going to be very familiar because as we graphed them in Unit 8, we talked a lot about what, on that parabola, what really represented the solutions, okay? So these are sort of our step-by-step guide. Our focus here when we're graphing is to, number one, write the equation in standard form. And when we write it in standard form in particular, we want to make sure that it's equal to 0. So if that's not already set up for you, that'll always be step one, is get everything on one side together, set it equal to 0, and everything, put everything on the other side. So always set it equal to 0 for solving by graphing. And then once you've done that, you'll graph that version of the equation that you have. This side right here, that's what you'll end up graphing to see what that parabola looks like. And then once you have the parabola in front of you, and we've mentioned this many times, you're going to look for those x-intercepts. Because you've heard me say this quite a bit, the x-intercepts are the solutions, are the roots, are the zeros. All of those things are synonymous. So if that's already sounding familiar, you're absolutely right. So today will involve quite a bit of review, but really it'll be a focus also how to use technology to help you find those solutions. So the solutions, the roots, or the zeros are those x-intercepts of the graph when you have it set equal to 0. That's the big idea today, okay? Now, because the solutions are exactly the same as the x-intercepts, that means that a parabola will have two real solutions if, when you graph that equation equal to 0, you see that it has two x-intercepts, meaning it hits the x-axis twice. For example, this picture down here, number 2. It will only have one real solution if, when you graph that standard form equal to 0, you realize or you see on the graph that it only intercepts the x-axis once. And there are some times where a parabola has no real solutions. And when that happens, you'll see that as you graph that equation, when it's set equal to 0, it never intercepts the x-axis, so it has no solutions. Either it would float kind of above it, or it would be below it, but it wouldn't quite reach that x-axis. That means that if you see no x-intercepts when you're graphing it, then that means it has no real solutions. So there's definitely that correlation there. So this is our end goal, right? We're starting off nice and easy. They give us the equation. It's in standard form. It is set equal to 0, and they've graphed it for us. So really, this is where you want to land. And most of the time we'll be talking about how to get here. But once you're here, the big idea is that when your equation was equal to 0, so write that down. When the equation is equal to 0, then the x-intercepts are those solutions. And so on a graph like this one, we just have to know where to look. You want to just know that you can look here and there, and if you can identify at what values of x this is hitting that x-axis, those are the solutions to that particular quadratic equation up there. And so based on this, it does appear that the parabola is hitting at a nice clean whole number, or integer I should say. So -1, -2, -3, -4. It appears here that x equals -4 is one of the, and x equals 1 is the other. Okay. If we try the same thing here, again, our focus is at what location is it hitting the x-axis here, and at what location is it hitting the x-axis there. Because once it's set equal to 0, that's all you have to worry about is where does it hit that x-axis. And so, again, this is counting by ones. It does appear to land in a nice clean number. So it appears here that the solutions would be at x equals 2 and at x equals 5. Okay, all right, so of course that was all essentially handed to you. So let's talk for a moment about how we get there, if it isn't already all simplified, or not simplified, but in standard form equal to 0 and graphed for us, right? Because step 1 is to write the equation in standard form equal to 0, let's go ahead and practice that for a moment. So when it says write the equation in standard form, our goal is to reorganize these if necessary so that it looks like this. All your terms are together on one side, your powers are in descending order, and you have nothing on the other side, so it's equal to 0. That's our goal. So if we look at number 3 here, you know, the x squared is already on the correct side, but that 15 is the issue. I want to get that over to the left and set it equal to 0. Pretty simple to do. We just do the opposite sign on both sides, and that gets rid of everything on the right, and I'll have nothing but 0 there. These are not like terms, so we'll just leave those next to each other, equal to 0, and I've met my criteria here. Okay, now you don't see that middle term. That means that b is 0, and that is okay. Sometimes you don't have all 3 terms, but as long as everything is together on one side and in the proper order, going from highest degree to lowest, and you have a 0 on the other side, you're good. Okay. Number 4, same thing. We want to get everything onto the same side, so I'll move the 14 with the opposite, which will be a positive 14, so that everything is gone on the right. So I have that negative x squared with that positive 14, nothing on the other side. That is now simplified. There you go. Try number 5 on your own. See if you can rewrite that in standard form. Okay, and on this one we do want to move the 5, but we also want to reorganize our terms, right? We want to keep our terms in descending order from highest degree down to lowest degree. So yes, we're going to move that 5, get rid of it there, so that all the terms are together on the same side. That means I'm now going to have a negative 5 on this left side. But in addition to that, I want to reorganize our terms, and these are in the wrong order. So this is a degree 1, that's a degree 2. We typically like to see the degree 2 first, or the highest degree first. So I'm going to actually write the negative 2x squared in front of that positive 4x, and then I'll finish it off with that negative 5 that I moved, and I have nothing on the other side, and now that really does match that standard form of a quadratic. Now the point of that was to practice that so that we can then graph it. So let's talk about graphing. So when we graph these, we're going to go ahead and create the parabola, but our focus, since we're trying to solve, right, is going to be about where is it intercepting that x-axis. So we want to write the equation in standard form if necessary, set equal to 0, and then we want to solve it by graphing. So the first thing I'll check is this in standard form and equal to 0? The answer is yes. So at that point, you can either create a table of values or pull up a table of values here on your calculator. So you might want to grab that, go into the y equals. We're going to graph this related parabola where it's equal to 0. So x squared plus 4x. Let's take a graph just to real quick get an idea of what that looks like. So there's our parabola. We're not just going to be like, oh, it kind of looks like that. We're going to use actual points, especially because we're very interested in where it intercepts the x-axis. So we are going to pull up a table of values, a good accurate graph here, and plot these, you know, when we plot these points. So looks like we have a point at -2, -4. Okay. We have a point at -1, -3. We have a point at the origin, and we have a point at 1, 5. So that's up here. Maybe I'll back up a little bit because I'm only seeing one side here. And then looks like I have -4, 0. 1, 2, 3, 4. And then also -3, -3. And last one, maybe I'll do is -5, +5. And I can see the curve shape, but more importantly on my table, I was able to see where those x-intercepts were, right? Because we know if we're on the x-axis, y is 0. So we can see very clearly that we have one x-intercept at 0 and the other x-intercept at -4. And when we graph it, you can see that that's where it hits the x-axis. So we'll go ahead and graph here so we can see what this parabola looks like. And then we can conclude that the solutions here are where x is 0 and where x is -4. So our equation was already in standard form. This is what the parabola looks like, and those are the solutions, which are the x-intercepts. Okay, let's take a look at number 7. On number 7, on this one, this is definitely not in standard form, which I'll agree. So we need to set it equal to 0. I could move the x squared to the right and set this side equal to 0, or I could move both of these to the left. I think I'm actually going to move this x squared to the right. There's no right or wrong answer here on this, but I do think that, first of all, it's only one thing I have to move, and then it'll also make it positive, and I kind of like that. So I'm going to add x squared on both sides and get rid of it here. So I'm going to have the 0 on this side, and then I'll have a positive x squared with a -2x and the +1. That's in standard form, equal to 0. So I definitely want to make sure I do that before I go reach for the calculator to get what this parabola looks like. Now that it's in standard form equal to 0, we can put it in our y equals x squared minus 2x plus 1. Graph it to kind of get a picture, because that always helps to know if we're on the right track as we're graphing. This is a great example of one that appears that it'll only have one x-intercept or one solution. Let's pull up some points that we can graph. I definitely don't want to graph anything like 49 or 36, or maybe even that one, but I can graph -1, 4. So I have a point at -1, 4. There it is. I have another point according to this at 0, 1. Let's see what else we have here. 1, 0, 2, 1. So 1, 0, 2, 1. And then let me see, we can fit another one here, 3, 4. 3, 4 works. So that'd be 3 over and up 4. That gives me a pretty good concept. It also shows me that single intercept, because I can see that right here again. When y is 0, I'm at my x-intercept, so it looks like at 1 is our only x-intercept. So we'll finish our parabola here, and we'll write our solution. And this is how you solve by graphing. You set it equal to 0 in standard form, and then you graph it and identify where those intercepts are. I'm sorry, that's not a 1. That's a 1, I mean. I was thinking of the y coordinate. So this particular one only has one solution, and it is at x equals 1. It's the only place where our graph intercepts the axis. Okay, so let's take a look at number 8. First question is that already in standard? Yeah, so this one is already in standard form. It's ready for us to go ahead and put in our calculator to see what this graph looks like. So if we enter the quadratic x squared plus 2x plus 4, and we graph it to get a view of it, this is our parabola. Now, we talked about this earlier in our lesson. We said if it doesn't reach the x-axis and it doesn't intercept it, then there will be no solutions. The x-intercepts are the solutions. When this is equal to 0, the x-intercepts are the solution. So this does not reach down low enough. So I already know the answer is here, a no solution. I can still graph it because we're still going to practice our graphing and graph the parabola. You were asked to graph, right? But we already know this is going to have no solution. So you could do a quick plot of the points that you see here. We've got, I think -3, 7 probably does fit here. So -3, 1, 2, 3, 4, 5, 6, oh, almost. So there's -3, 7 up there. I have a point at -2, 4. And there's that one, at point at -1, 3. And another one at 0, 4. And another at 1, 7, which will be also off the page. So you can see it its vertex stopped here at 3 and then turned right back around and never came down far enough to actually intercept the x-axis. So no solutions here. There's our parabola for evidence. The equation was already in standard form, and this has no real solutions. Okay, so that gives you some good practice there. Now, let's talk about cubics for just a moment. We're not going to talk about this a lot, but the idea here is just to kind of give you a preview or an expansion that if the solutions are where the graph intercepts the x-axis, then it's not limited to just quadratics or just parabolas. It doesn't matter what kind of polynomial function you have, okay, to find the zeros or the solutions. The big thing here is that the name of the game is just still, it is still all just about the x-intercepts. So write that down. Okay, so even though these are not quadratic, excuse me, if you know where to look, you can still come up with those solutions. So this happens to have 1, 2, 3 x-intercepts, so I expect to have 3 solutions, and all I have to do is list the x values where those are located. So according to this, it appears that there's a solution at 0, there's another solution at x equals 1, and another solution at x equals 2. So that has 3 solutions. This one is not a parabola and it's not quadratic, but it only has 2 solutions. Looks like it has a solution here at -2 and one at 1. Try number 14 and see what you get for that one. Okay, if you said you had a solution at -1 and at +1 and at 3, you are in good shape. So you can see that when you're graphing these and looking for the solution, it's really all about the x-intercepts. Our focus, of course, will be on quadratics, but you can see here, just you have a little taste here. It could be just about anything. Okay. Now, this is where it really becomes pretty powerful. All of the ones that we did for just for the last examples played very nice, and those intercepts landed quite nicely on whole numbers that were easy to read and easy to graph, right? But that's not always the case, right? The world isn't always quite that nice. And sometimes you graph a parabola and it has solutions, but it is really difficult, if not impossible, to identify that location or that solution from a graph just with your naked eye, okay? Just by looking at it. The moment that that intersection happens between 2 numbers, we really begin to just kind of play a guessing game. So that would be a real issue for us, except we have a great piece of technology that can really help us get the exact ones, even if just us manually looking at it, we cannot tell. This will calculate them for us. And again, I believe I have, already kind of shown you guys this in the past when we were working in Unit 8, but it's a really good review to get us practicing what the calculator can help us do. So let's try number 1. They've already, this kind of goes back to the first few there where they've already given them to us in standard form and graphed. So we just have to know where to look. But unfortunately, even looking here isn't going to help us because it doesn't appear that it lands on a nice whole number. So let's find out where these are exactly. We want to round the answers to the nearest tenth. So that's the accuracy level we'll use. We've got x squared minus 3x plus 1. We'll graph it. It should look a lot like this guy, and it does. Okay, and I want to know exactly where those are. And in fact, I might zoom in a little bit and use the same X and Y window here, just so that I have a little bit more space for what I'm about to do. That's always pretty smart to kind of match what the picture has. So this appears to go from -3 to 5. So on the x-axis, I'm going to go from -3 to 5 on my window. And for the y-axis, I'm going to go from -3 to 5. And now it should be a much closer match to what I see here. Okay. All right, so there's our graph. Now I want to know exactly where that location is and where that location is. And I've shown you this, I think, a couple of times. We're going to go to this calc menu right above trace. So second calc. And what we're after is those zeros. That's just another word for x-intercepts or solutions. So we'll select the second choice. Now you got to do one at a time, and you have to give it those walls or those boundaries. So let's say I want to start with this one first. I want to get just to the left of it. Okay, just a little bit to the left. Hit enter, and then get to the right of it. So get to the other side. You're kind of hugging it with two borders there, or boundaries. And then it's going to say, okay, I'm going to look between those two markers you made. Am I ready to guess? And you hit enter a third time. And when that word 0 comes up, and you can see that it's like, oh, the y-intercept is, the y-coordinate is 0, so that is your x-intercept. That's how you know you're at your solution. And if we round that to the nearest tenth, I would agree. I would think it's just 0.4 there. So one of our solutions here is at 0.4. And now we do the same thing for the other one on the other side. So second calc, we're going to select that second choice. We want to get close but stay to the left of it. So about right there maybe. We'll hit enter. It kind of sets up that first sort of imaginary boundary. Then we'll get to the other side of it. Hit enter. So now it's kind of made two sort of boundaries or walls that are and the point is right in between. It's ready to guess. I hit enter one more time, and there is my other intercept at 2.6 when we round. So the other solution is right at about 2.6. Okay. Try number 2 on your calculator. See what you get there. Okay. So for number 2, hopefully you tried it. If you got on your calculator x equals negative 1.3 after rounding and x equals 2.3, then you are in good shape. Okay, those are your solutions on number 2. All right, let's go on to the word problem. So it tells you here of a toss in bocce ball can be modeled by this equation here, where x is the horizontal distance in feet. So x is the horizontal distance and y is the height. So if you think of it that way, this is our horizontal distance, like how far out, and this is our height, how high up. Okay, and that's our parabola. So the first question is, how high does the bocce ball bounce? Right. So let's say that it does a quick bounce. If we think about this, right, we have this bocce ball kind of going up and back down. If we want to know how high it bounces, we're looking for the max of this particular parabola. So let's find out what that is. We've got negative x squared plus 4x. Let's graph that. I might need to adjust my window. Oh, actually, that's not too bad. So this is our height. So if we want to know how high up it bounces, we want that max height. We can calculate second calc, maximum. That's our fourth choice. Again, get close to it, but give it a left boundary. Get on the other side to the right of it, give it a right boundary, and then let it guess. So according to this, my max height is 1.9999. Oh, no, sorry. My max height is my y, sorry. So it's 4. So we're looking at a height on the y-axis of 4 feet. So the bocce ball bounces 4 feet high in the air. Okay. How far away is the bocce ball when it lands? So now think about that. This is my ball. You know, it bounces, it goes up, it goes back down. If they're asking me how far away it is when it lands, it's asking me for the x coordinate of that landing point right there. So it's really asking me for that x-intercept. Okay, so we'll go to our second calc. This time we'll want to find that x-intercept, 0. We'll get a little closer to it, but stay to the left. Hit enter. A little on the other side of it, to the right of it, hit enter, and then hit enter one more time. There it is. So it's 4 feet away where it lands. So if I were graphing this, that highest point was 4 feet, and it's landing back down at 4 feet. So it is 4 feet away. Interpret the x-intercepts of the graph. Well, let's think about that. The x-intercepts are where it hits that x-axis. Okay, well, that's where my height, my y-axis, is 0. So it must be when it was, or how far away it was when it was on the ground at the beginning, and then how far away it was when it was on the ground when it landed. So the x-intercepts are where it starts, or where the bocce ball starts, and where it lands. Okay. Okay, we're going to finish off with this one, and then on the back side we've got a little bit of a regression problem, but we've done regressions before, so it'll be pretty much review, and we'll do that one in class. So let's see, on this one we have the opening of a tunnel through a mountain can be modeled by this function right here, where h is the height of the tunnel in feet from the edge of the tunnel at ground level. So we've done a few like this. What is the width of the tunnel at ground level? So again, we've done a few like this. If we have a parabola somewhere along this, and we have the tunnel opening come back and down, go up and back down, if I can find those x-intercepts, then the width of the tunnel is the distance between them. So all I have to do is graph this, find out what is this x-intercept and what is that x-intercept. That's where the tunnel starts from the ground and where it ends at the ground. And whatever the distance is between those x-intercepts, that must be how wide, the distance of how wide the tunnel is at that ground level. So let's go ahead and enter that in our calculator. This is our function here. So we've got negative 1/30 x squared. I know it's f, but we're going to use x for the calculator's purposes, and then plus 2x. Let's go ahead and graph that. I might need to adjust my window now for sure. So let's actually go to a standard window. We're going to go zoom 6. So that zoom, middle zoom, and then the 6 will get us back to a negative 10 to 10, negative 10 to 10. This definitely still isn't even close. So let me make sure I entered this correctly. I did. So I just need a whole lot more. I need a whole lot more distance on the x and the y. I don't need distance on the negatives, which kind of makes sense. Negatives really wouldn't make a lot. Maybe I'll go to 50 here. So a lot less negatives because those aren't very necessary. I'm going to go up to 50 feet. Let's see what this looks like now. Okay, now we're getting a better view. Definitely don't need quite that much height, but I definitely need a little bit more x here. So let's maybe make this go to 100 and maybe a little bit less height. Ooh, that's pretty good. Okay, so again, I'm interested in those intercepts there and there. I'm going to adjust my window one more time because I don't quite need to go all the way to 100. And just to get that window a little bit easier to get, I'm going to give it a little bit more bottom so I can hug with those boundaries. Okay, so I want to know where it lands there and where does it land there. Let's do that. Second calc. We're calculating those zeros. We're going to get just a little bit to the left. Oh, there's my cursor at the very top. Gotta just let that come all the way down to the left of that first intercept. There we go. And then to the right of it. And then I'll let it guess. So the first one's at the origin. Okay, so this one's 0. This is kind of the starting point. That's totally fine. Let's now look for the second one. Second calc. We're going to look for that 0. We're going to get close to it, but stay to the left of it. Almost, 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 almost. There we go. Yeah, that's pretty close enough. Still to. And now let's get to the other side of it, to the right. Enter and guess. The other one is exactly 60. So I have one intercept at 0, the other one at 60. The difference between those is my distance. So if I subtract that, of course I get 60 feet. So what is the width of the tunnel at ground level? The answer for that is it is 60 feet wide. Okay, and then we'll do the regression work tomorrow in class together.